Hey, physics class, I'm going to introduce you to Coulomb's law and give you a sample calculation and then ask you to do one of your own. So if you remember from way back, we talked about gravity. I wrote Newton's gravitational equation. It looked like this. Force was equal to some constant times, times, there we go, the product of two masses divided by the square of the distance between them. This is called an inverse square law. It's proportional to both masses, and you just need to have a constant there so that everything works out to be in the units. Well, it turns out that this inverse square law is just a feature of energy spreading out in three dimensions, because Coulomb's law looks almost exactly like it. There is a force again. This time the constant is represented with a lowercase k, and instead of being proportional to mass, electrical force is proportional to charge. Don't blame me, but charge is represented with a q. So the first charge is going to be Q1, the second charge is going to be Q2, and then again it's separated by the square of the distance between them. You can see the similarity between the two equations. It's just a different proportionality because the forces have different strengths and they are proportional to charges or masses. That's the difference between them. Okay, so we don't need to worry about this. Let's just get into this. What is the value of that constant, that k? So that k, it's equal to 8.988 times 10 to the 9th. And the units are Newton meters squared per Coulomb squared. Okay, so what is this? This C. C here refers to the unit of charge, Coulomb. That's the basic unit of charge. Now, the way that it works out, electrons and protons have the same magnitude of charge, it's just an opposite sign. So because a single electron or a single proton is the smallest unit of charge that an atom can have, then we can just refer to the elementary charge. That marker's not doing too well, is it? Let me see if another one's going to do better. There we go. So elementary charge, lowercase e, because it's the charge of the electron, of course, 1.6022 times 10 to the negative 19 coulombs. You can round it to 1.6 for easily remembering it, so you don't have to keep looking it up. Okay, so clearly that is an infinitesimal charge, very, very small charge that a single electron has. So basically nothing ever has a charge of an entire Coulomb. It's just too much. That's like a million trillion electrons. The amount of force required to keep all of them in one place is just astronomical. So you're never going to encounter something that has a charge of 1 Coulomb. Okay, so there is some more about this I'd like to show you, but we will do that later. Right now, I'm just going to give you an example and then an assignment. Okay, so let's do the electric force on an electron by a proton. You'll notice that I wrote this, it's positive. That's because that's just the elementary amount of charge. if I were going to have the charge of an electron, I just have to put a negative sign in front of it. Okay, so let's determine the magnitude and direction of the electric force, say, on the electron of a hydrogen atom exerted by a single proton. That's the atom's nucleus. So I'm going to go to a new page. So make sure that you have those equations written down, those constants, so that you can work out this example. And then you can do your assignment. Okay, so we've got a hydrogen atom. That's going to be a single proton. There we go. There's our proton. And it has an electron. Yeah, that's a great circle. There's an electron orbiting it. There we go. Just make sure those are visible. I don't want that to get washed out by the light. Okay, so there is your hydrogen atom. Okay, and this has a positive charge. This has a negative charge. They both have the same magnitude of charge, though, 1.6 times 10 to the negative 19th coulombs. And we also need the distance. So in our equation, this constant is something we have to look up. These two charges are things that the problem has to give us, and that distance is something that would be part of the problem also. So what is the radius of a hydrogen atom? It's actually, well, as you might guess, very small. 0.53 times 10 to the negative 10th meters. Noticing this marker not doing too well. Oh man, do you think markers are an essential supply? I'm gonna get in trouble for going out for markers. Oh no. All right, well, let's see, where am I? So I just noticed, I'm copying this off of an example, that this number is not in proper scientific notation. Shame. Anyway, so that's the radius of a hydrogen atom, 0.53 times 10 to the negative 10th meters. So if we were to put everything into the equation, it's going to look like this. The force is equal to that constant K, 8.988 times 10 to the 9th. I'm going to leave the units off so it fits all in one page. Okay, that's K. Now I have to multiply that by this fraction. So the charge of the proton is 1.6 times 10 to the negative 19th. The charge of the electron is the same thing, but it's negative. Say, what is a positive times a negative, class? It's a negative. So what do you think a negative force is? It would be an attraction instead of a repulsion. Okay, and so we got K, Q1, Q2. Now we just need R squared. So that would be the square of 0.53 times 10 to the negative 10th. I don't know why I changed from parentheses to brackets, but there you go. Okay, so this right here is a scientific notation nightmare. If you're going to enter this into your calculator, be super duper careful. Make sure that you put parentheses in all the right places. Okay. Negative 19 on the top, that's going to be an exponent of negative 38. But then we've got negative 10 squared on the bottom, so that'll be negative 20. And then there is a 9 over here. So the exponent is like going down almost 40, but then going up almost 30, just to give you a ballpark to see if you're off by like a factor of a couple trillion. The answer to this turns out to be 8.2 times 10 to the negative 8th newtons. That is an extraordinarily small force. 8.2 times 10 to the negative 8th newtons. But it's worth remembering that when we're talking about force equals mass times acceleration. And when you consider that the force on something very small can cause a great acceleration, the mass of the electron is 9.11 times 10 to the negative 31st kilograms. So even though that force is really tiny, when you consider the mass of the electron, negative 8 exponent on this side, negative 31 over here, to get from negative 31 all the way up to negative 8, like the exponent of this acceleration is going to be 23. So it turns out actually that force is extraordinarily huge on an atomic scale. Anyway, that is your example. Please check the news section of the LMS and the links for what your assignment actually is. All right, good luck, and email me with any questions.